We were talking about instability that is noted on the attachment line of a swept wing, and this is the schematic. If you look at a top view, it would look like this. The oncoming free stream q infinity subtends an angle alpha drawn with the normal along which we have the u infinity, right. The projection of q infinity along the normal to the leading edge is u infinity, and there is a spanwise component w infinity going there. So, this is your plan view, right. In this plan view also we show how the streamline which is outside the shear layer looks like. So, external streamline refers to a streamline which is outside the shear layer. So, what you note is that the component, the u component that we call as the streamwise component, and the w that we will call as the cross flow component have different relationship at different height. So, what happens is as a consequence you have streamlines which may be aligned in this direction or at the wall, and as you go outside you can see the cross flow component keeps changing, and that actually skews or twists the streamline, and the external streamline is the one where the w component has come to 0 and u has reached its free stream value. Okay. So, from that point onward your streamline would be the same, but inside the shear layer it is all twisted. That is what we are trying to show you here by showing a isometric projection of the velocity profile over the wing. Now, what happens along the leading edge, that is what we call as the attachment line. So, this is your attachment line, and you draw a plane normal to that along the attachment line is called the attachment line plane. And in that attachment line plane what happens? You have a flow in the spanwise direction. So, since that is the flow direction, so we call that at itself is u, and it has no other component. And this problem that I was telling you about also when performed experimentally, what you actually end up doing is you have a, let us say, wind tunnel wall like this, and you fit in a kind of a swept wing which will connect from wall to wall. The idea is not to have any of the stiff vortices and which will affect the flow in the near vicinity, but you do it in a wall to wall fashion. And then of course, you will have this structures, vertical structures forming there that sort of migrates along the spanwise direction. You would also have similar such vertical structure created here, corner vortices here, but because the flow, oncoming flow is so this is what we are, let us say, drawing there as q infinity, right, and that we split it into u infinity and w infinity, right. That is what we are talking about. So, essentially q infinity is like this. So, that is composed of this two component. So, this component is what we are calling as u infinity, and this we call it as w infinity, and this is your q infinity. Okay. So, what happens? This is far away from the wing, but in the attachment line plane what happens is you do not have this normal component. The flow is in the spanwise direction. So, that is what we are calling that itself as the streamwise component. So, the flow that is in the spanwise direction is the flow direction. So, that is why there is a kind of exchange of axis system. That is why you would notice that we have identified that axis as x 1 and z. So, why x 1? X 1 is the external streamline fixed coordinate system. So, viewed from external streamline, that would be the x 1 direction, and from the wing fixed direction that would be your z direction, because that is the span direction, right. That so, basically it is a kind of a description that we are talking about, that viewed from a geometric perspective that is the spanwise direction z, and viewed from the flow direction that is actually streamwise direction. So, that is why you notice that we have called it simultaneously as x1 and z, right. We have to be very clear about this, and you can understand then from the flow perspective, this is the, because the flow is in this direction. So, this will be a spanwise direction. So, this we are writing as z1, but from the geometric perspective it is the x direction. So, that is what I thought I will spend a little extra time and explain to you that this subtle aspect of it. So, now that we understand this, it is pretty much clear what we are talking about. So, we have a plane, attachment line plane, that is where the flow is from here to here in this direction, and over that the flow wraps up on top, and below that attachment line flow wraps on the bottom. So, that is your visual picture. Okay. Now, let us see what happens to this. I told you that it was once again Prandtl who always does things before everybody thinks. He suggested that we can look at the governing equation, governing Navier-Stokes equation, and then consider the flow to be occurring over a swept wing, but whose span is infinite. So, that means what? You have still a flow in the geometric perspective in the z direction, but the variation with z is 0. That is your meaning of infinite swept wing. So, you will have a z component of the velocity, but the derivative with respect to z will all go to 0. So, that is your infinite swept wing assumption. So, Prandtl said let us consider the flow idealized like this and then see what happens to our equilibrium flow itself. So, if you look at it this way, so z axis is parallel to the generator of the body, because that is what it is, like a body of revolution kind of a thing, such that all flow derivatives with respect to z can be omitted in the governing differential equation. So, this is your x momentum equation. So, this is we are writing in wing fixed coordinate system. So, we are writing it in the wing fixed coordinate system. U is the velocity component in the x direction, v is the velocity in the y direction, and then what is this term? You can recognize it, this is the pressure gradient term in the x direction, and this is your viscous diffusion term. What have we done here? Of course, we have taken a boundary layer approximation, so that the streamwise gradient is diffusion is negligible compared to wall normal diffusion. And what happens to the z direction? Of course, because of infinite swept assumption, that term is 0. If del u del z is 0, all its derivatives also will be 0. So, second derivative automatically falls off. So, that is your x momentum equation. Look at now your, you do not have to do anything about the y momentum equation from the boundary layer equation, right, we know that. And look at now the spanwise component, the z component. So, you have u del w del x plus v del w del y equal to nu times the wall normal diffusion of w, right. So, this is okay. So, there is no applied pressure gradient in that direction, whatever it is there, it is in the streamwise direction, and this is your continuity, and you can very easily see that del w del z is 0 because of infinite swept-in assumption, right. So, this is the equation, and now let us go ahead and try to simplify it. Oh, before you do that, note down the boundary condition. At the wall, all the 3 velocity components are 0, and when you go far away from the wall outside the shear layer, u would approach capital U and w will approach capital W, right. And now if I now try to solve those equations, those two momentum and the continuity equations subject to these two boundary conditions to get the equilibrium state, Cook actually thought of extending what Faulkner and Skan had already done for flow with pressure gradient. We have talked about Faulkner-Skan profile. So, Cook basically extended that same idea, that here we are talking about a infinite yawned wedge. So, if the flow is like this, so you have a wedge here, okay, but that is infinite in this direction, right. So, that if you are looking at 0 angle of attack case. So, basically the wing itself, that attachment line plane itself, I am considering there is a wedge there, okay, and the flow is coming right at the leading edge of the wedge. And then we can prescribe the variation of u like what you do in Faulkner-Skan profile. It goes as x to the power m, okay. And what? W in quantity, because we are talking about infinite sweep. So, we have a w component, but it does not vary with z. So, that is why you have the other value there w as equal to constant. So, from now on what we would be talking about, that we will be talking about extension of Faulkner-Skan wedge solution by this idea of Cook as Faulkner-Skan-Cook profile. So, okay. So, we will be talking about Faulkner-Skan-Cook profile. So, we are basically looking for the description of this Faulkner-Skan-Cook profile. So, what we do is we go through that same exercise. We define stretch the wall normal direction by introducing eta. M is some kind of a pressure gradient parameter like what we have done, remember. M would be something like x by ue due dx. That is your pressure gradient parameter. So, that is what it comes here, and you scale it by this kind of Re by square root of x kind of thing, and it is the y coordinate that is stretched. So, you are stretching that way. You also define a stream function. What is the idea here? Of course, when you introduce a stream function, then in the xy plane you do not need to worry about mass conservation, it is automatically satisfied. Existence of psi will give you that. And we are talking about a spanwise component of the velocity, because outside the shear layer w is a constant, but inside what happens? It will vary. That is why we saw the streamline skews. So, we introduce another non-dimensional dependent variable g of eta, and this psi we define it with respect to a non-dimensional stream function f of eta. So, basically we are trying to depict the flow in terms of two quantities, a stream function which is given in terms of its non-dimensional value f, and a non-dimensional spanwise velocity component which is given in terms of g eta. So, this is how we would go about describing the flow in terms of two new dependent variable. You substitute those things, those two definitions of psi f and g, and plug it in the governing equation that we have just now seen. What you would find that the momentum equation will yield this one, the x momentum equation will yield this first equation, and this is what something you have already seen. This is exactly like what we have obtained for Faulkner-Skan profile also, and beta is the combination of this term 2 m by m plus 1 that appears there. It is a nonlinear equation, all right, but in the leading term it is linear, and the z momentum equation gives you this equation. So, what you notice, of course, directly from here that f can be solved independent of g. So, first you will be solving for f by solving 10. Once you have the f, you can plug it in 11 to get the g. So, So, this should possibly help you in defining the flow field. So, what happens is you need to solve these two equations. These are ODEs. So, it is a third order ODE. So, you require 3 conditions for F, and second order ODE in G will require 2 conditions for G. These 5 conditions are obtained through this. At the wall, you have psi equal to 0, psi prime equal to 0 with respect to x and y. They are 0. So, that translates into f and f prime equal to 0, and similarly the w component is 0. That gives you directly g equal to 0, isn't it? And then when you go to the edge of the shear layer, what happens is the streamwise component reaches a value of 1, the spanwise component reaches that constant value. That is it. So, both of them f prime and g approaches 1. So, now we do a little bit of jugglery, because what have we gotten so far? We have gotten the mean flow. If we solve those two equations, that will define our capital U and capital W, right? Capital U and capital W. Now, if you go back and see what is this theta naught. Theta naught, we defined it as the angle between the external streamline and normal to the leading edge. So, let us go back and take a look. So, that is what it is. If you look at the plan view, so this is your x axis, wing fixed x axis, and this is the projection of the external streamline on the plan view. So, this theta naught is the angle between the two. Okay. So, if I do that, so I have a component of x component that I am calling it as capital U of y. Then I have a component that is capital W of y, and I am trying to find out the component along x1, y1 and z1. So, this is essentially the whole idea. So, I want to get it in the wing fixed coordinate system. So, that is what we are doing here. So, we have obtained U and capital U and capital W. We know what this angle theta naught is. Then we can obtain this component in the external streamline fixed coordinate system. This is what we get. And you can realize that y and y1 are the same, because they are perpendicular to the wall. So, you do not have to distinguish between the two, and you have obtained the velocity profile. And what happens along the attachment line on the leading edge of an infinite swept ring, we know UE, the edge velocity, happens to be proportional to x itself. This is exactly like what we did for stagnation profile, if you recall. Well, you may have done it in some earlier courses. I did not. Did I do it? I think we did not do it in this course. The stagnation point profile, the Hemans flow, we have not done it. But if you look at Hemans flow, that is what you would notice, that there would be UE would be equal to kx, and V would be some ky with a minus sign. But in this case, what happens? You do not have a y component there. So, you have this, and this is directly proportional to the x component, whereas WE is equal to W infinity itself, right. So, because once you are outside, the flow does not change anymore. That is the definition of infinite swept condition, that WE will remain same. There is no additional span-wise pressure gradient. That is the whole idea. So, once we have this edge condition provided for UE and WE, we could now think of the attachment line that it divides the flow into two. One part follows the upper surface, the other follows the lower surface. And if I now focus my attention on external streamline coordinate system, x1 now coincides with the attachment line. That is what we discussed, that x1 and z are same, right. That is what we are saying. And the boundary layer edge velocity in this external streamline coordinate system would be given by this. u1e should be equal to q infinity sin phi. What is phi? Phi is the sweep angle. Phi is the sweep angle, right. What happens to this? This has to be equal to 0, because you are in the streamline direction. So, you cannot have any other component. Flow is along the streamline. So, that is what you have here, and there is no cross component. That is it. And the angle between the external streamline and normal to the leading edge is given by tan inverse of W e by U e. So, this is again going back to your wing fixed coordinate system. So, the wing fixed coordinate system component defines your theta naught. Okay. Now, so you understand, u1e means the edge velocity in the external streamline fixed coordinate system. W1e is external streamline fixed coordinate system, and that is by definition has to be equal to 0. But that is not necessarily the case when you look at in the wing fixed coordinate system. There you would have a streamwise component and you would have a spanwise component. So, this is how we are going to define the flow field. So, what happens? We have written down that expression for u1. If you recall, let us go back there here. So, if I know this two quantity cos theta naught and sin theta naught, then we are done. Okay. What is it? We have already seen tan theta naught is W e by U e. So, what will be cos theta naught? So, we will substitute it there, but what about u? That also we can define in terms of f, right. We have the definition of psi. So, we can differentiate it with respect to y to get u. So, this will be substituted in terms of f prime cos theta naught. We will use this expression sin theta naught, we have it, and this also we can define it in terms of g. Right. So, if we know this, then there is no problem, because then we can go ahead and we are going to get this. You can very clearly see that u of y is nothing but f prime times u e, because it's u by u e is equal to f prime. Then I have this cos theta naught, and w is nothing but g times w. And if I define u1e as this, that is that, because once you have the wing fixed component and now you want to go to the external streamline fixed component, that only has u1e component. W1e by definition is 0. It will be equal to this, isn't it? So, let us substitute all of that here, f prime cos theta naught u1e, I have just written it like this, and this will give me this component f prime cos square theta naught plus g sin square theta naught. Okay. In the same way, you have the other expression that is given for w1 component. If I non-dimensionalize with respect to u1e, then I get this. Okay. So, you can realize that we will solve those two ODEs. So, we will get f and g distribution, and from those information plus UE and WE information, we will have the expression for theta naught and we will get this. So, once we have the flow direction components, then we are ready to define the equilibrium flow, and that is what we want to do. Now, look at the attachment line itself. In the attachment line itself, what have we seen? We saw UE is kx, whereas here we said that UE goes as x to the power m. That was the Faulkner-Skan's idea, and that was extended by Cook like this. So, what you find here, m is equal to 1, right. If m is equal to 1, what was beta? Beta was 2m divided by m plus 1. So, if m is equal to 1, beta is also equal to 1. That is what we are saying. And what about the angle? What is the angle between external streamline and the normal to the leading edge? It is 90 degrees, because the flow has turned. You see, the one part is going up, another part is going down, and in this plane it is going in the span-wise direction. That is why x 1 and z are synonymous. That implies theta naught equal to pi by 2, right. So, what happens is, we can use this information in the previous slide. What we have seen the expression, what will we get? The streamwise velocity is just simply given by g, okay. And the cross flow profile is equal to 0. So, what happens? This is the magic of Prandtl. He has shown that the flow is two dimensional, because you have only one component of velocity, the other component is identically equal to 0. Okay. So, that is what it is. Of course, you see it, right, because the W1 by U1e is that f prime minus g into sin theta naught cos theta naught. So, what happens for 90 degree, of course, this goes to 0, that is what we have established. So, W1 is 0. What about U1? You will get this part go away, only this part will be there. So, what happens is, you will have a two dimensional flow on the attachment line plane, but you will be solving those two ODEs that we have seen already. First, we will be solving for f and f prime from that Faulkner-Skan-Cook equation, and from that we will go to the second equation, that was g double prime plus f prime g equal to 0, that we will be solving. So, we will get g, and then from there we have gotten U1 and W1. Well, you see that this was what was established by Prandtl himself. So, we notice that this profile is purely two dimensional, and you can do a little bit of computations and then calculate the shape factor. The shape factor is 2.54, which is slightly smaller than the Blasius profile. So, that means what? Of course, it will be more stable. Smaller the value of h, more stable it is. You saw that flow with adverse pressure gradient h keeps rising, right. So, you would see that, and this is what is obtained, that if I calculate Re theta critical based on momentum thickness, this is about 235, which is higher than Re theta equal to 201 for the Blasius profile. So, this is slightly more stable, right. But you understand now, this is the attachment line plane. It is not a stagnation point flow, it is different, because the stagnation point flow for 2D section, we have seen that Re delta star critical value reaches a value which is greater than 10,000 as compared to Blasius profile of what 520. So, that 520 actually corresponds to R e theta equal to 201. Okay. And so, you can see that this attachment line plane is not as stable as the stagnation point flow. It is slightly more stable than the Blasius profile. This was what we pointed out. Now, having defined the equilibrium flow, we can start thinking of its stability. How do we do that? Before we do that, if we are looking at the instability of the attachment line flow of the swept wing, let us look at what people have noted experimentally. For example, Paul, DIA Paul did that experiment, and instead of taking a wing, he took a yacht cylinder, and he noted that along this attachment line in this plane. So, if I have this plane, in this plane, of course, there will be a lot of vertical structure, because aided by the swept angle, they will propagate inside the shear layer or outside the shear layer. So, that is what is being said, that experimentally it was noted that attachment line vertical structures are very much there. So, we decided to investigate the subcritical instability by looking at the role of convecting vertical structure in explaining this leading edge contamination problem. And what we would be able to do is we have defined the equilibrium flow, but now for defining the instability of the attachment line flow, let us solve the 2D Navier-Stokes equation. Now, I mean, that will be all inclusive. The flow itself is 2-dimensional, and then we will find out its instability by solving the 2D Navier-Stokes equation. So, there is no assumption made except the fact that we are talking about the disturbance field also being 2-dimensional. We are not talking about 3D disturbance field, and we are not talking about invoking Square's theorem or anything. It is just that we are studying 2D instability. Okay. So, now the situation is something similar. So, if I project this flow, I mean, if I look at it like this, the flow will exactly be the same thing that we have done, studied before. We will be talking about a flow in a box, and there is this vortices, they are going in this direction. That is what the experimental observation of Paul, Fenninger, everybody have looked at it, Arnold, they have reported the existence of convecting vortices in the attachment line plane. So, we follow the same thing that we have talked about just now. In fact, we are discussing this attachment line instability as an example of that vortex induced instability. So, that is the whole idea. So, solve the Navier-Stokes equation. These are the two governing equations, stream function equation and the vorticity transport equation. And here the RE that we are having here is defined in terms of the velocity scale that is given by u1e. If you recall, that is the edge velocity in the streamline fixed coordinate at the edge. So, that we have calculated, and the length scale we have purposely taken as some kind of a see your attachment line boundary layer would be somewhat like this. So, you take this as your delta. So, this is your length scale. That is what has been used in defining this Reynolds number. Okay. And you would completely agree with me that for a 2-dimensional flow, stream function and vorticity formulation is the most accurate one, okay? Because you do not have any scope for spurious mass generation, etc. Existence of psi does that, and the vorticity is a higher order quantity which you are directly solving. It is much better than solving, let us say, the primitive variable and then converting those u and v components into vorticity. because there if I get a solution of a differential equation as u and v and then numerically differentiate to get omega, that accuracy will be compromised as compared to directly obtaining omega from a differential equation, right. So, that is what we like to emphasize. There are other mathematical issues, that vertical field also happens to be divergence free, because it is a two dimensional flow. So, it becomes automatically divergence free. Why? Because omega is in the z direction, divergence of omega in the xy plane is of course 0, because omega is not a function of x and y. So, that is a very significant plus point, right. While if you solve for primitive variable formulation, and although by definition the vorticity itself again is in the z direction, and again it will be divergence free, but the magnitude of the vorticity calculated will depend on numerical differentiation of u and v. That will be a shortcoming of that formulation. So, what we do here is the same thing. We are studying the flow in a, well, this is basically a straight line. We take 501 equidistant points in this direction. So, this is our streamwise direction, right. So, this is your streamwise direction, and this is the wall normal direction that we are studying. So, this is essentially your leading edge of the wing. And in this direction we had taken about 101 stretched point in the boundary layer. In this JFM paper that we reported some results. Show you some result, one can do any number of calculations. There were these two papers that we talked about. One was in the computers and fluid, where we reported the computational result, and this paper, this JFM paper, where we talked about the physical mechanism. In those publications, you would see there are many cases computed, but I will just show you one particular case of convection speed of about 20% with respect to the free stream, and think of the height of this vortex is about 30 delta star. Okay. This height is slightly more than what we had done in the experiment, where we had taken something like 27.5 delta star. So, we will look at it and then see what do we get, how stable or unstable this is with respect to the Blasius boundary layer. Okay. So, we look at some representative results. The top frame is shown, for which the vortex, one of the vortex, a periodic vortex we are studying, it is right outside. Please understand that even this numerical experiment that we are reporting here, it is a basically unit process. We are trying to find out if a single vortex passes by, then what its effect is. That is what we are calling as vortex-induced instability. And in this kind of experiments, what we are talking about, it is not necessary just only a single vortex passes by. You get a stream of such vortices getting created here and swept away like this. So, each one of them will have its footprint. So, what we are noticing here is a typical output of such footprint. So, in an actual flow, it will be a sort of a convolution of all these results taken together. But we are trying to establish by a numerical unit process what this is like. And in this case, what you notice that this vortex is still outside the inflow. So, if I take it like this vortex could be somewhere still outside, and it has started affecting the flow inside. How does it do it? Of course, it does do it because through this inflow boundary condition, and the top of the computational boundary you have some imposed condition that shows the effect of the approaching vortex, and you can already see bulge there indicating the flow is being affected. And you can now that answers your question whether we have a constant shear layer thickness or not. It just simply starts affecting it somewhere here. Unlike the Blasius boundary layer case, what did we see there? We saw two sites of instability. One was at the leading edge. Here there is no question of leading edge. We are talking about infinite things. So, we have just simply taken a small slice of it, right. So, there is no leading edge site in consideration. And what did we see there in the Blasius profile also? That it is selective. It does not happen anywhere but at a fixed location. And what was that fixed location? That is what we are doing through the assignment. We are finding out at different x's the time history of pressure gradient. We will be able to find out why and where and it occurs and what value of C it is the most potent. So, that is the essence of the assignment that you guys are doing. So, what you are going to report back to me is a specific nature of the Blasius boundary layer. Quite unlike here, you will not have that. Here, things will have to essentially start from the leading edge itself of the computational domain, right at the inflow, and we are starting to see that. And then as it approaches near, then you can see that it just breaks up into all those wall normal vertical eruptions. And this is a solution at t equal to 6, 7, 8 and various times are given. I think the third frame is at t equal to 1001, then the last frame is at 2001. So, that is what you see, that the vortices are sweeping past, and then even in this case what has happened? The vortex may be still somewhere here, but the disturbances are swept away. This is due to one vortex, but there is no guarantee, or it would really be likely that by the time this has gone away, this another one is coming back in its trail. So, there would be a repetition of these events, and this is what we need to do. This also tells you, if you are an aerospace engineer, that how you would go about designing a trouble-free wing. What would you like to do? Remove the source of disturbance. We have seen, right? We have been talking about it all through, that there is no such thing as generic instability. We have seen for pipe flow, the flow can be unstable at 2000 Reynolds number based on diameter. It can be even at 100,000, depending on how you quench the background disturbances. So, here also the boundary layer may be ready, but if I do not allow this convecting vortices to be created, I am done. So, basically if I am trying to design a wing, I would pay particular attention in that design where this convecting vortices, this corner vortices are not created at all, or if they are created, they go at a weaker strength, and also there is a selectivity of C that you can actually take a look at that paper, that computers and fluids paper, where we have done some 7, 8 cases. Take a look at there and you will find out the receptivity of the boundary layer for different C. So, what we just now saw, we can make this following comment. The first frame corresponds to an early time when the convecting vortex is left to the left and out of the computational domain, and its influence was seen as an upwelling of the shear layer near the inflow. By the next frame, we saw the convecting vortex has appeared over the computational domain, but we also see a very intense sequence of instabilities over the attachment line. And if you look at the last one, this is where the location of the vortex was. However, the leading edge of the coherent structures, those are getting created due to this vortex instability. They are out of the computational domain. So, you can see that it also goes at a very fast clip. So, that is the reason that when you start designing aircraft wing, you want to do a sort of a conservative estimate. You always assume the flow to be turbulent right from the leading edge, because if you do not stop the flow of these convecting vortices, it is very likely the flow will become turbulent right from the leading edge through this mechanism. we are not talking about how this leading edge vortices affect the flow over the wing surface later, but here we are just keeping our attention focused solely on what is happening right at the leading edge itself, on the attachment line plane itself. Now, we also noticed that such vortices create an adverse pressure gradient. If it is counterclockwise, it creates an adverse pressure gradient ahead, the action of scouring. That is what we explained, right? It tries to lift off the shear layer. At the same time, behind this vortex, what it does? It tries to push it down. So, what will happen? You will see a kind of a thinning down of the shear layer, and that is what we saw in the last two frames. Wherever, so looking at the last two frames itself, you can kind of tentatively guess where the vortex is. Where the vortex is. The vortex, like what we are seeing here, there is a thinning down on the here. So, the vortex must be somewhere ahead of this. So, on this side it is creating instability, on this side it is thinning down the boundary layer. And rest of the place where its effect is marginal, you can very clearly see that it is almost like a constant thickness boundary layer. And here you are also seeing the same thing, but now here what has happened, that it's created a significant thinning down, because it is acted over a longer period. See, this is about 1500, this is 2000. So, over a longer period, the same favorable pressure gradient has acted upon. So, please do not try to view it like the usually the eigenvalue analysis always looked at, that what happens is you have a time independent equilibrium flow, and the instability is one of how the disturbance grow in space. However, in this solution of Navier-Stokes equation and the attendant description that we are talking about, we really do understand that there is time element playing a big role. That is what we are doing, right? We are calculating the pressure gradient as a function of time at a fixed location, and we do see that. We see that very clearly, that here, well, it was getting affected here. Here also you could see the vortex is somewhere here. There is a little bit of thinning down, and here it is. You can see it has thinned down a little more, and here the thinning down is marginal. But as time progresses, you can see this is the trace of the free stream vortex. That is why we did not even mark by arrow, if I wanted you to understand that. But here in this part of the shear layer, it has acted over a longer period, and that cumulative effect shows a significant thinning down of the boundary layer. Now, this is what we commented upon. Now, we did talk about this, that we have looked at a very particular case of gamma v in terms of this, that corresponds to a chord diameter of 6. Okay. The first bubble occurred at a location where the Reynolds number based on the displacement thickness is about 190. So, that what was the RE critical? It was noted as 235. So, if I see instability event occurring at 190, that is obvious that it is a subcritical event, right. So, that is what we are saying. The flow criticality indicates a subcritical instability. And this is something we have all along seen in vortex-induced instability. Once the primary instability makes its appearance through the formation of a first bubble, a succession of many others will follow. They will be ahead of it, right? Because locally, if the shear layer bulges out, it creates a further adverse pressure gradient ahead of it, right? That is what you do. You do see a intensification or cascading effect of this adverse pressure gradient. And this cascading phenomena occurs at a very, very phenomenally high speed. And that's why the contamination just simply sweeps across. So once you have attachment line shear layer, which is slightly more stable with respect to the linear mechanism, it is of more interest to investigate this bypass mechanism of LEC. We can actually talk about this. This can actually provide a very nice basis for future investigation, which we have not been able to do. Suppose I define this solution of Navier-Stokes equation in the attachment line plane as the inflow of a calculation where I could do something like this. Let's say this is the leading edge of the wing and this is my attachment line plane. So now I could do is I could basically study the instability over the wing. This solution as a function of time can come from what we have done just now, right? So it's like creating your inflow condition, and then you can study that. You recall this is what we talked about, that we talked about the necessity for first seeing what happens on the attachment line and then subsequently what is its effect downstream on the wing. So that part of the investigation is overdue. Maybe somebody will like to do that, and it is going to be a very fantastic piece of work, because most of the analysis or the research result, those are available in the literature. You basically split the flow into two. Either you look at the streamwise instability or you look at the cross flow instability. But if you do a complete 3D analysis, you are going to see a combination of the two. So you don't have to make any assumption. You are going to get a truly space-time dependent 3-dimensional instability study. Okay? Maybe I am giving you an idea for doing some future research work for yourself. Now, we reiterate that instability is only feasible when the speed of this train of convecting vortex. Remember, we did that case where we have periodic vortices. That we established there. We also considered a periodic vortex. There also we found out that you basically have to have a speed which is lower. Why? Because you recall, you are now seeing it, right, in your disturbance stream function expression. What is important is u infinity minus c. So that's why your c has to be less than equal to u infinity. That gives you a large amplitude. So that also, you will notice that for a periodic vortex also, c has to be distinctly different from u infinity, right? That's what we are saying. But there are the differences. One of the main differences, of course, in this case, periodic vortex case, you impose a space and time scale. Here you don't. In this case, also we said that lower speed of convection has higher receptivity. That we have seen with the help of those expressions for disturbance stream function. And we have shown that you can sow the seed of bypass transition. This was not possible. There was this case, computation by Obrist and Schmidt. They had some earlier inkling about what we have done in our fast track paper, that the vortex induced instability is important. So Schmidt was involved in studying in bypass transition, so he asked his graduate student to look at it. What he did was basically this, that you have this flow like this, and then created two vortices, one going in this direction, another going in this direction, and both of them were set equal to c equal to infinity. See, look, I mean, there is a qualitative difference between what we did and what they tried. They tried to do it, study it as a 3-dimensional problem, and they put this convecting vortex outside, but that was forced to go at resting speed. That is why they did not see any effect at all, very, very marginal effect. We can actually explain what we did. It was in the attachment line plane itself, and we can show that disturbance energy does get created significantly if you do convect the vortex which is not going at this. So, I think we will stop here and we will take up from this point in the next class.